In this video, we review how to use transformations to sketch functions. So we're going to start with this function here, sketching y equals -3 bracket 2 bracket x minus 1 close bracket squared plus 4. Now this looks very daunting at first, but just a reminder of some of the work that you would have done before to be able to sketch this. So in order to sketch this, we first need to realize that there's a parent function here, a related function that we can look at, and that related function here is f of x equals x squared. And we can see that because the squared is here. So the variable here is x. We can see that there's something happening here with the x, but it's ultimately being squared. So we are going to sketch this f of x equals x squared, and then we can use transformations to help us out. So just to remember, a reminder, pardon me, that y equals x squared looks sort of like this. I'll put some points in roughly here to give you a sense of what that looks like. So 0 squared is 0, 1 squared is 1, 2 squared is 4. So we get this familiar parabola shape. And we'll just try to sketch that roughly. Alright, so that's the x squared portion. So the question then becomes, how do we deal with all of this other stuff in here? All of this extra stuff. So I'm going to start by looking at, let's look at this function here, g of x equals -3 x squared. So we're going to just break this up into little bits and pieces and try to sketch those little bits and pieces. So really what this is saying, and just a reminder, maybe we should look at a table of values, at least to get us started. So we had -2, -1, 0, 1, and 2 that we sketched. And when we did that, we ended up with 4, 1, 0, 1, and 2. Well, this function here, g of x, is saying take the x squared values and multiply them by -3. So why don't we add a column here and see what happens? Well, if we take this value here and multiply it by -3, and this value by -3, and so on, we end up with something that looks like this. -12, -3, 0, -3, and oh, I made a mistake here. Sorry about that. That should have been a 4. So when we multiply that by -3, we get a -12. So just a reminder, this was g of x. This was -3x squared. So when x was -2, y should be -12. That's off my graph, but somewhere down here maybe. Maybe I'll change colors so we can follow along a little bit better. When x was -1, y was -3, so that's over here. When x is 0, y is 0, and we just kind of repeat on the other side. So we get this kind of stretching happening. This is what we call a vertical stretch, and hopefully that's coming to you. It's also reflection in the x-axis. So the negative here causes that reflection in the x-axis, and the 3 causes a stretch vertically so that the graph kind of is pulled out and down. You can imagine it being drawn on a balloon and holding the top of the balloon steady and pulling down on the rest. So that's that part. Let's look now at a different function. Let's look at the next sort of step in this progression. So h of x equals -3 times 2x squared. And again, we could make a table of values. I almost wonder if this needs its own video, video on its own to kind of look at that. Oh, and I'm sorry. Let me just fix that up. I just realized I put the squared in the wrong location, so let me fix that up. Should have been outside the brackets. This becomes a little trickier, but as a reminder, this value inside the brackets, we're going to take 2, multiply it by x, and then we're going to square that value. So what that does is it actually causes a horizontal compression. So instead of dealing with a vertical stretch or compression, now we're dealing with a horizontal compression by a factor of 2, which means all of the x values get cut in half. Let's see if we can do that in a different color. So remember here x was 0, so it's going to stay at 0 because half of 0 is 0. X here was 1, half of 1 is a half. Y value doesn't change. Same over here, and then down here, this y value was 2, so we would get this kind of point that looks like this. And so our parabola looks sort of like this. And again, that's a compression horizontally. So we're taking the graph and pinching it in by a factor of a half. All of the x values get cut in half. And then let's keep moving along here. Let's look at what that plus 4 does at the end. Let's call this k of x. Negative 3 times 2x all squared plus 4. Just a reminder that plus 4 means take all of the y values that you had from here and add 4 to them. So that means that the graph is going to shift up 4 units. And this is getting to be a little bit messy. I almost wonder if we should do this on a separate grid. So let's see if I can slide, maybe make a copy of this and slide it in here somewhere, maybe a little bit smaller. So just a reminder, we had something that looked more or less like this. Let's shrink this one up a bit. Or slide it out of the way. Make it so we can see what's going on here. So our graph looked sort of like this. I'll draw the red one again. So it was here at 0, 0. It was half and negative 3. Negative a half and negative 3, and then we had the other point, which was negative 1 and negative 12. So somewhere down here is what we had. So then we're going to take all of this and we're going to shift the whole thing up 4 units. So all of the y values get 4 added to them. So we end up taking this whole graph and shifting it up 4, which will look something like this. So a reminder, here we are at x equals 1/2, y equals negative 3. So when we shift that up, we should be at 1/2 and 1. And we get a graph that looks more or less like this. Harder to draw on this smaller scale than I thought it would be. And then the last little bit here is, we'll call it m at x. And so m at x equals negative 3 bracket 2 bracket x minus 1 squared plus 4. And what that does, the minus 1 does here, is it actually shifts horizontally left or right, and because this value is a 1 here, we're going to shift to the right. And again, it's a little bit confusing here because it's kind of opposite of the sign here that you might think, but if you make a table of values, and as I said, this may be worthy of another video, if you make a table of values, you'll see why that is in fact the case. So what we're going to do is we're going to take that graph and slide it 1 unit to the right. So I don't know if I can just grab the whole thing and slide it. I could if I drew it all as one continuous piece. So basically just take everything and slide it over 1. So we get something that looks, whoops, more or less like this. This is just a rough sketch just to remind you of how to do this. And so that's how we can use transformations to sketch these sort of functions. And again, this is something that you've looked at for a while now. Started looking at it a couple of years ago, and now we're continuing. And then last year you would have looked at, well, what happens if it's not a parabola? What happens if it's not a quadratic function? What happens if it's a root function or something else like that? Before we get into that, though, what I just want to remind you of is that it's really important that you do the stretches, compressions, and reflections first, and then you perform the translations, so the shifts. So basically the A and K have to be dealt with first. So what I've done here in this part is I've just written, sorry about that, just written the function notation that we just had written down right in here. But instead of using the parabola, I used f to represent any function. And we'll talk about that in a minute, but it's helpful maybe to talk about what all of these parameters do. So the A, this value right here, was the shift, vertical shift. Sorry, not a shift. It's a vertical stretch or compression. That's the word I'm looking for. Vertical stretch or compression. It was also a reflection in the x-axis if it was negative. So this also drives the reflection in x-axis. Pardon me. Reflection in x-axis. The k value out here, it was a horizontal stretch or compression. So that's what was responsible for those. Horizontal stretch or compression. it also did a reflection in the y-axis. Now we didn't really look at that, but that's what would happen. We get a reflection in the y-axis if it's negative. The C value out here, this was a shift up or down. Translation. And the D value was a shift left or right, or translation left or right. And this is true for all functions. So we looked at it as an example with a quadratic function. You would have looked at it before with other functions. So as I said, we could actually do the same thing here. Let me just copy this. And instead of putting the f in, so we had it like this, where we didn't have an f. Whoa. We didn't have an f. We just had the squared out here. So that is our function. It's the squaring. But I can also say, well, instead of the squared function, I want this to be the square root function. Or instead of the square root function, I want it to be, let's try that again. Just going to try to make another copy. I want it to be a sine function. So we could actually replace this f with any function, and all of these rules still apply. So I might say, hey, I want this to be a sine function, or a absolute value function. It doesn't matter what that function is. We take the sort of base function, what it looks like, and we apply these transformations as we would any other time. So that's a very sort of quick review of function transformations, and just reminding you of how to sketch a function from the base function using those function transformations.